Hi there, physics students. I'm Mr. Grams, and in this video, we're going to look at Newton's laws, an introduction to forces, and all the things that goes with that. There are 7 checkpoints that you're following along with in your checkpoints packet. So please make sure you pause the video whenever we get to a checkpoint and answer those questions, and then come on back and start it back up again. Here we go. We're starting out with the definition of force. A force is defined as a push or a pull. This is something you do all the time, usually with your hand, pushing something, pulling something. Could be in any direction, positive or negative. And we use newtons, named after Sir Isaac Newton, to describe it. Capital N is the symbol for the unit. Capital F is what we use to identify a force. If we have more than one force acting on an object, we want to talk about the total or net force acting on the object. And for that, we use the symbol sigma F. That sigma means sum. It's a Greek letter. Sometimes you hear it called the unbalanced force or the average force acting on an object, but it is in total the vector sum of all those forces. When we're talking about forces, it's important to know that we're talking about interactions. A force doesn't exist without an object to act on and something causing that or doing that. So if you think about this structure, your hand pushes the button, the stick pushes the ball, your arm pulls the string, the arm pulls the rope pulls the crate. There's a thing doing the action, and there's a thing feeling it. So here's our first checkpoint. Pause the video, do the questions under checkpoint 1, then come on back and resume. All right, the next topic here is inertia. You've probably heard the word inertia before, but it means something very specific in physics. And in physics, it is the tendency of an object to resist its changing state of motion. So objects, we don't see them naturally just speed up, slow down, or change direction. They tend to go in whatever motion they have and keep going. Inertia is completely dependent on mass. In some ways, they're interchangeable words when we're talking physics and motion. Something with small mass has a small or little inertia. Something with a large mass has a large amount of inertia. So this leads us to Newton's first law of motion. An object at rest tends to stay at rest, and an object in motion tends to stay in motion with the same speed and direction, or the same velocity. Newton's first law basically says, as long as there is no unbalanced force or the net force is 0, objects will continue in whatever state they are in. So what does this actually mean? From a graphical perspective, this could be when the forces are balanced, the net force is 0, it's either moving at a constant velocity or at rest, which is 0 constant velocity. Checkpoint number 2, pause the video, answer those questions. All right, our third piece we need to talk about is mass and related ideas. So mass, usually given the symbol little m, is the amount of matter in an object. And that's something you probably know from chemistry. Think about how many atoms make up something. This is really what we're thinking about when we're thinking about mass. Mass does not change no matter where you take an object. It's measured in kilograms, or kg, one of the fundamental units we use in physics. But here we have an example. Baby Java is on 3 different planets, and in all those cases, the mass of Baby Java is 12 kilograms. Does not change no matter where you go, because Baby Java's mass is just how much matter Baby Java is made out of. On the other hand, we have the weight force, or the gravitational force, or the force of gravity, or the weight of something. And these things are all terms for the force of gravity pulling on some amount of mass. Weight is a force. It is measured in newtons. And so that's something we need to kind of keep different from mass. The weight force is based on the pull of gravity, the pull of the earth. So it always pulls you down toward the center of the earth. Weight force, just like all forces, is an interaction between objects. If there weren't 2 objects, there wouldn't be a weight force. So the person and the earth is the interaction, or the earth and the moon, or Baby Java and the planet are those interactions. Gravitational force depends on where you are, what planet you're on, and how that planet behaves. So weight force depends on the mass, but also things to do with how far apart these 2 objects are. We'll learn more about that later. But if you notice, on all 3 planets, Java's mass still remains 12 kilograms. But if we calculate the force of gravity, it's that mass times little g. And little g on each planet is different, so we get different forces of gravity, different weights. It leads us to checkpoint 3. Pause the video. When you're done, come on back. All right. We want to connect this idea of forces to the idea of moving objects. We've already said something about it. It turns out when things are not accelerating, that means that the net force is 0. So that net force is 0, not accelerating, are talking about the same thing. This is, again, either at rest or moving at a constant velocity. On the other hand, accelerating objects must have a net force that is not 0, an unbalanced force, to cause this. This could be speeding up, slowing down, or changing direction. And this leads us to Newton's second law. Unbalanced forces cause acceleration. If we have a net force that is not 0, we will get an acceleration. Exactly how much acceleration depends on the mass. You often hear this referred to as F equals ma, or net force equals mass times acceleration, or F net equals ma. And this is just saying that if you unbalance the forces, if you have a net force, objects will accelerate. So if we compare the two, right? We've said these things before, but the net force is 0 and net force not 0 is the fundamental thing we're looking at, is the difference between the first law and the second law. All right, that leads us to checkpoint number 4. Moving on to our third and final of Newton's laws, Newton's third law. It's described as this: when one object exerts a force on a second object, the second object exerts an equal in strength and opposite in direction force on the first object. This is often called, for every action there is an equal and opposite reaction. You may have heard that. But in this case, the person pushes on the wall with a force, and you see that the wall is pushing on the person with an equal and opposite force. We call these two forces action-reaction pairs of forces. The action is the man pushing to the right on the wall, and the reaction is the wall pushing to the left on the man. You'll notice they have kind of this parallel structure. Thing doing the pushing or pulling, direction, object pushing on, and then flip them the other way. There are 5 rules, quote unquote, but that describe how action-reaction pairs work and how you can understand whether you're talking about Newton's third law or something else. The first and most important one is, unlike the previous 2 laws, the forces that we're dealing with here have to be on 2 different objects, the wall and the man in this case. They have to be the same kind of force. A force of gravity and a normal force or whatever doesn't really apply here. They have to be equal in strength. That's the magnitude, the number of newtons of force. They have to be in opposite directions, and they have to act at the same time. This is in the cartoon where you smack something and then they react a few seconds later, and then suddenly anyway. So here's some examples. The earth pulls down on a person. Well, the third law pair example would be that the person pulls up on the earth. Baby Jabba pushes down on the table, and the table pushes up on Baby Jabba. Checkpoint number 5. 2 more checkpoints to go. So here we have common types of forces. If we just labeled every force as F, F1, F2, F3, it could get confusing. So we have some names for different types of forces that are very common. The first one is the force of tension. All forces get a capital F, pretty much, and then they get a subscript indicating what kind. In this case, capital T for tension. Anytime you have a rope, a string, a cable, anything like that, it is a force of tension. So here we see a crane holding on to a wrecking ball with a force of tension. Then we see a little pendulum being held on to the ceiling by a tension. We see a little kid pulling to the right with the force of tension on a wagon. Another type of force is an applied force, and this is what we use whenever someone, animal or human, takes a hand or a foot or something, but touches an object and pushes or pulls. That's usually what we call an applied force. 2 other types of forces that are helpful to know. The normal force, capital F, subscript N, is from a surface. And so if we go back to our example of the man pushing on the wall, there's actually 3 different normal forces. The force of the wall pushing back on the person, and then each foot feels a normal force pushing up from the ground. These forces are always perpendicular to the surface, which, if you remember your geometry, is what normal means in this case. Perpendicular to a surface. They are normal forces. The last kind of force that we'll define today is the spring force, and this is applied to an object whenever a spring is compressed or stretched from its natural length, the length it would be with nothing pushing on it. Second to last checkpoint, checkpoint 6. All right, the last thing we need to talk about is how we put all this together. And that is the free body diagram, or a dot diagram. A free body diagram shows an object as a dot. You know, as physics teachers and physicists, we really like to simplify things. Just a dot represents any object. And here, this is just the result of some image search for free body diagram. And you see they all are a little bit different, but they have some features in common in every case. And the kind of 4 rules for free body diagrams is that the object is a dot. It can be a big dot or a small dot, whatever you need to draw your diagram well. All forces acting on the object are shown. If it's a force, it needs to be on this diagram. All forces are drawn straight, starting from the dot, and they're all straight arrows acting outward from it, pointing in the direction that the force acts. And so how does this look? Well, if you have a weight or gravitational force on a slug, the slug must be in free fall because there's only the force of gravity, straight down toward the center of the earth. If the slug is sitting on a floor, there's a perpendicular normal force from the surface, which in this case is up, and the force of gravity is pulling down. Here's the slug swinging as a pendulum from the ceiling. The force of tension is along the string, and the force of gravity still points down. Here's an applied force. Someone is kicking a slug. The applied force is at the direction of the kick, and the force of gravity is straight down. You'll notice that in these cases, I've shown the forces acting where they act on the picture, but on the free body diagram, they're all acting on the dot. The spring force, here we have a spring pushing up on the slug and the force of gravity pulling down on the slug, like so. All right, that's the end. Final checkpoint. Make sure you've answered all those questions, and we'll talk more about forces as we go in this class.